or depends if you want the sigma square, so it's n divided by n, or the sigma. If it's the sigma, so you divide it by square root of n.
Okay, it's not the correct answer, but it's a good try. Anyone else? From Wikipedia?
No, but we took it
No,
from
yeah.
Zohar slides. This is something we took from the slides.
Zohar didn't write the solution for the question.
No, but he
In
said
slides.
he writes for the CLT how it looks.
Yeah, but the whole question here is what is a standard or the variance of CLT Markov chain.
Of this Markov.
Yeah, but what is the formula for the variance? This is the question.
I had another question.
You can ask and then answer the question. Michael.
Then maybe I'll answer first. I don't know.
Okay.
So according to Wikipedia, I guess the mean should be the mean of the underlying distribution, and the variance should be the original variance over n squared, right? The sample variance over n squared, if I recall correctly. I can open Wikipedia and check again. And what I wanted to ask was,
No, that's what they asked.
No, I think that the variance is the same as in the CLT of the, because it's uniform.
Did you check your answer?
what, as in calculating?
Yeah. If you answer a question that you know the solution, then this is a solution, right? You wrote some formula, you have a solution in for some state. Okay, did you check it?
We saw
You, someone that answers the bonus.
No, but we saw that it is related.
It's a good practice to
that
check
is
your
related
answer.
to n.
Huh?
We saw already in the.
Yes,
That
it
it related-
will be related to n.
This is
Yeah.
why we put n.
Okay, but did you check your answer?
That was in another bonus.
Check your answer.
Yeah, you should have told us.
No, I checked. We know.
That's really
So,
unfair.
okay, the solution is a bit different. The solution is this. And the solution says that
All right.
the variance of the CLT, of the Markov chain,
No matter which Markov chain.
I think it's no matter which Markov chain, but especially those Markov chain.
When it's uniform.
Okay, make it on the phone.
אני יודעת את זה, אבל הקובעת.
I think it's for every Markov chain, but we can check later. This is the variance of the first distribution, okay, and this is the covariance, the sum of the covariance of the first distribution with the relevant distribution.
The
What
stage.
is the first and
mean
what
the-
is
Relevant, the I distribution,
What is the first?
the initial distribution.
So,
Which
But
is,
they are all
Uniform in our
identical.
case.
but they're identical
But
and
they are all
they're,
identical.
but the covariance
What
should be
identical?
zero.
This
What identical?
They converge to zero.
No.
What identical?
When they station.
Each
The
stage.
distribution on each is
Yeah.
Uniform.
in our case, because it's stationary.
What is the distribution in each step?
Uniform.
Not
One of us.
it
Ah.
depends on what state you were in.
Yeah.
Okay, so what will be?
No, what do you mean? We started with the initial distribution was 1/6, right? Uniform for everyone.
Yeah, this is here.
And for the given transformation matrix, x2 is also 1/6. So maybe I didn't-
Yes,
No.
yes. Yes.
No,
The expected is the average.
okay.
No, not
but
the average.
but also the distribution. Because
The
You might.
the marginal distribution. The marginal distribution you are correct. The marginal distribution is always uniform. But the joint distribution is different, and covariance is a property of the joint distribution. How will I calculate the covariance? I'll calculate the covariance in this way. The expected value of x dot y plus minus of
EX squared times EY.
EX times EY. What is EX and EY?
Same.
3.5.
3.5. So this is 3.5 square always. Okay, how can I calculate this?
1 over all this.
Yeah, average it
On what?
on all possible values.
Of what?
P of x, y.
The first x.
Of the transition matrix.
Right?
With the transition matrix.
Yeah.
So in the first step, we have the transition matrix here. Okay?
But you have the
Order-
probabilities of
In
moving.
order to calculate this,
You
what
times the-
do I need to do? It will be the value of x multiplies the value of y
times the probability of having each one of
times
them.
the probability of x multiplied by probability of y.
No multiply because it's depends.
X and y.
Yeah.
The probability of x and y is written here almost. Why? Because this is not a joint distribution. The sum of the numbers here is
One.
no.
Yes, it's
No,
one.
that's not
It's
true.
not one. The sum of all the numbers is
Okay.
6. So in order to convert it to
You
joint
divide.
distribution, I need to divide it by 6. And in the second step, what will be the transition matrix?
The same square.
The matrix squared. And in the n step, it will be the matrix in power of n. And I always need to divide it by 6.
But this matrix converges to a matrix of
This
six,
matrix converges to what?
1, 6 everywhere.
Yes. Or in other word, the covariance is
Uniform.
converged to
0.
0. So when I'm answering a difficult question, the first step is to answer the question. So if you answer, maybe I will give you a point, maybe not. But the second step is to check your answer if you can do it. Okay? So in this question we have mu 3.5. The variance of the initial distribution is 35 over 12. For each I, the joint distribution is t in the power of I multiplied by 1 over 6. So now we will run an experiment and we will get the same result. And as you can see here, okay, I'm do the experiment 2,000 times. Okay, I'm calculating the relevant matrix divided by 6, and then I'm calculating the covariance of each columns. And then I'm using this covariance in order to get the variance of n and the standard deviation of n. This. Okay, and then I'm treating the standard deviation. I'm getting the exact number that I got in the experiment.
Yes, but this
Very
is why it says that if you take n enough big, then it is like the normal, and this covariance is actually like independent, and this covariance is zero.
If n is big enough,
And if n is big,
Right.
yes, and this is our situation. This is why we use this.
yeah, but first of all, I don't know if you answered it correctly or
No.
not, but probably you didn't do
We
this.
didn't do this, of course, but I know that
But
we
you
know.
can check your answer. Now you know how to do it.
No, we know that it converts to zero, the covariance.
Okay.
This is why we didn't put the covariance in the answer.
Okay, so let's see now a different example of 20. We know that in 20
20 is
it
not
needs to be 0.7, so let's run 20 and we will get,
Because it converts very fast, we have to do it with 5.
no, we got 0.7 in the experiment and 0.73 in the, not in the experiment,
Okay,
in
but
the
and-
theoretical
But you
calculation.
can't say that n 20 is a big number.
Okay, but I can say that the covariance has influence in the beginning. Okay?
So it doesn't
And the
convert.
covariance converge from some n to 0. It's okay. But if the n is not big enough, or if it not big enough from a normal perspective, big enough from covariance that converge to 0.
The intuition here that the covariance
There
converges
is
to
no
zero.
intuition.
Just a second,
okay?
just
I answered it the same. Actually,
Just let
not
me
with
understand.
Not with Wikipedia, with Zohar, but it's the same.
the covariance converges to zero. Is the indication is that we're getting the stationary state, or it's completely different. mean,
No,
because
the indication is the stationary state, the uniform distribution. Yes.
mean,
If you are getting not
if it doesn't
the stationary
change,
state, you are getting the
There is
uniform
some
matrix. You will get the uniform matrix. Or mean identical matrix, or the value will be the same. Then the covariance is zero.
So
Because
practically,
multiplication of the probability will be
the same.
Yeah.
so the fine print of the CLT says if we start at the stationary distribution, then as n is very large, I'm going to get the standard deviation and the mean and blah blah blah.
Okay.
Is it true that it's not practical? I mean, that if I don't know the stationary distribution, if I haven't calculated or whatever, then I'm never going to get there. So say I start with some initial distribution that's not the stationary one, then all that's going to happen in my Markov chain, even for like a million steps, is I'm just going to converge towards the stationary one.
If you have one.
Assuming there is one, but I'm never going to start my converging series that is going to apply for the CLT. Is that a correct? Because in that case, if I haven't calculated the stationary distribution, then I'm not going to be able to make like a very large simulation
Yeah,
and
but
rely on the
here,
CLT.
here in the theoretical part,
Yep.
I started from initial distribution, not from the stationary distribution. It's in our case, it's the same distribution.
I'm pretty sure. I'm going to check it, but I'm pretty sure like the CLT did state that I have to start with the stationary distribution.
I don't remember. Okay, but in this case, the stationary and the initial are the same.
Right. So in our question, we were fortunate enough to start with.
Obviously, I can start from the second. What will be the second distribution?
T times my initial distribution.
Exactly.
Right.
And what will be the second transition matrix?
No, T squared.
Okay, so I can start there.
Right. But what
If I
I'm saying
start
is-
there,
What I'm saying is, had I not started with my in my stationary distribution, would this ever converge? I need to check that what I said was correct, that I have to start at the stationary.
in order to Markov chain to converge,
Yeah.
I need to check it. I don't remember.
Okay.
So I tested our wrong theory, and it gives the same result as the.
I don't know how you tested it, but
I just took the data. What is the STD? This is basically what we said.
took what data? You can't create data and test your answer.